Hi Bobcats! In this video we're going to look at how we can use bond enthalpies to come up with an estimate for the delta H of a reaction. The key to this process is to recognize that when bonds are broken, you have to put energy into the system. So that means it's endothermic, the delta H's have a positive sign. And when bonds are formed, it's an exothermic process. And so that energy is released. And so there's an associated negative sign with any bond that's being created. If we're trying to estimate the delta H reaction from bond enthalpies, here's our basic process. We're going to figure out all of the bonds that get broken in the course of the reaction and add up the bond enthalpy for all of these broken bonds. This is recognizing that breaking bonds is endothermic, so all of those numbers will have positive signs. And then we need to account for every bond that gets made in the course of the reaction and subtract the bond enthalpy for all of these created bonds, because making bonds is exothermic. For our first example, we're going to look at the reaction of ethylene with chlorine to make 1,2-dichloroethane. When this reaction takes place, we are going to basically think about taking this chlorine molecule, the Cl2, and breaking the bond between the two chlorine atoms. And we're also going to break this double bond that's between the two carbon atoms. Those are the bonds that we're going to break. Now, just to kind of sketch out in a different color here, what's going to happen in between each carbon or each chlorine atom is going to form a bond to carbon. So we'll make a bond there, and then we'll make a bond, over here. That was not very pretty. And then we'll also form a single bond back in between these two carbon atoms. So now let me kind of mark this up a little bit differently so that we can keep track of everything. So in terms of the bonds that we are breaking, we're going to break the ones that we have in red. So that'll be a carbon double bond to a carbon. And then we're also going to break a chlorine with a single bond to a chlorine. Now, when the product is formed, we are going to create, I'll put I guess an M for the ones that we're making. We're going to make a carbon-chlorine single bond right there, and right here we're going to make a carbon-chlorine single bond, and then we're going to make a carbon-carbon single bond as well, because we broke the double bond in our breaking process. So over here, to tally up the bonds that we're going to make, when we make it, it's exothermic, so we have to subtract the value. We're going to make a carbon-carbon single bond, and we're also going to make two carbon-chlorine single bonds. So we'll have to double that value. So if I go to the table of bond enthalpies at the Sapling Learning Compendix, or I look up that table in the previous video, the carbon-carbon double bond has a value of 611 kilojoules per mole. The chlorine-chlorine single bond has a value of 243 kilojoules per mole. And then for the bonds that we are making, it's exothermic, so we're going to have a negative sign. And the carbon-carbon single bond has a value of 350. And then we'll have two of the carbon-chlorine bonds that have a value of 330. And since those are being made, again, we're going to have to subtract that value. And so if we take those numbers and we run them through a calculator, let's see, we've got 611 plus 243 minus 350 and minus 2 times 330, which is negative 156. There we go. In this example, we're going to estimate the delta H of reaction for nitrogen reacting with chlorine to give NCl3. And to really see what it is that we are doing in terms of making and breaking bonds, we really need to look at the Lewis structures for all of these compounds. Kind of an interesting thing with this reaction is that we are breaking every bond that we have over here on the reactant side. So we're going to break this nitrogen-nitrogen triple bond. We're going to break all of these chlorine-chlorine bonds. Once we have all those bonds broken and we reassemble the molecules for the products, we are going to make every bond that's over here in the product. So we're going to make these bonds between nitrogen and chlorine. Okay, so now let's get into the bookkeeping side of this. How are we going to account for all of these bonds? Well, in terms of the bonds that we are going to break, and remember breaking is endothermic, so these will all have positive numbers with them. We are going to break a nitrogen-nitrogen triple bond, and we are also going to break 3 chlorine-chlorine bonds. In terms of what we're going to make, and making is exothermic, so we're going to put negative signs with these bond enthalpies. We are going to make bonds between nitrogen and chlorine. In fact, every bond that we're going to make is between nitrogen and chlorine, so that's 6 bonds. So we'll take a -6 times the nitrogen-chlorine bond enthalpy. Okay, so let's look up the numbers for these. For the nitrogen-nitrogen triple bond, this is a really stable molecule, so it has a very large bond enthalpy, 941. And then we have 3 times the chlorine-chlorine bond strength, which is 243. And then we are going to make 6 of these nitrogen-chlorine bonds, which each have a bond enthalpy of 200. So let's run all of that through the calculator and see where we end up at. So we have 941 plus 3 times 243 minus 6 times 200. And that gives us a delta H of the reaction of about 470 kilojoules. So our estimate of delta H of reaction for this reaction is 470 kilojoules. If you look closely at this reaction, you might notice that this reaction is 2 times the formation reaction for NCl3. To have the formation reaction for NCl3, we need to have a coefficient of 1 out front. And so if we were to divide all of the other coefficients by 2, we would end up with the formation reaction for NCl3. I went and looked up the numerical value for this reaction and discovered that it is, let's see, so delta H of formation is 232 kilojoules per mole. Well, this reaction is half of the reaction that we estimated the delta H for down below. So if I take that 470 value and divide it by 2, I'm going to do that down here at the bottom. 470 divided by 2, I get a value of 235 kilojoules per mole. Now that's pretty darn good agreement, because remember that when we're estimating enthalpies of reaction this way, it really is an estimate, because the numbers that we're using for the bond enthalpies, like this 200 over here, the 243 or the 941, those are estimates based on an average strength of an NCl bond in a wide variety of molecules, so while this technique of estimating delta H of reaction using bond enthalpies is a pretty good estimate, it's not quite as accurate as using something like Hess's law and a tabulated set of values of heats of formation. However, particularly when you start getting into more complicated molecules, or if you are a researcher who's working on synthesizing brand new molecules, that thermodynamic data may not be available for your molecules, and so you are left using approximation techniques like what we just did with breaking and making bonds in order to get values for your enthalpy of reaction. Before we wrap up this chapter, I just wanted to real quickly go back to something that we talked about on the very first day of class, which is called Bloom's taxonomy. And Bloom's taxonomy is something that the people in the College of Education use to talk about how people learn things. And I want to talk about the thing that is the highest level on Bloom's taxonomy. Back when I was taking education classes, we called this synthesis. Bloom's taxonomy has been revised, and I think today this generally gets taught with the phrase creating. The whole idea of synthesis, or with creating, is that it's the most challenging thing to do. And in the context of chapter 10, what we're doing is putting together all sorts of things that we have already learned in a new way. And just as an example, our previous chapter put together gas laws and reaction stoichiometry. We were using moles as the connection between those two things. And in this chapter, we put together a bunch of stuff. We put together Lewis dot structures, we put together bond enthalpies, we put together Hess's law, and delta H of reaction. I want you to be aware that general chemistry will continue to combine concepts across chapters all the way through to the end of General Chemistry 2, or Chem 1342. And frankly, this process will continue throughout all chemistry classes that you might take. And when you're putting together these concepts that you've learned before, but in new situations, you are operating at that highest level of Bloom's taxonomy. So that's quite an accomplishment. Give yourself a pat on the back for getting all this stuff figured out. So our objective was to try to estimate delta H of a reaction by using bond enthalpies. We were basing this on the idea that it is endothermic when you break bonds, and it is exothermic when you make bonds. And so if you can account for all of the bonds that are broken and all of the bonds that are made in the course of a chemical reaction, you can come up with a pretty good estimate for delta H of a reaction.